Hi. So we're getting very close to the definition of Fourier, so series. So we have to recall, I have the set of L2 of minus pi pi. Says this is a set of function from minus pi to R, well, to C, we said. Says these are measurable. And we define such that integral from minus pi to pi of fx squared dx is smaller than infinity. And then we define the inner product fg to be 1 over pi integral from minus pi to pi of f of x g of x bar dx. And the induced norm, L2 norm, is norm of f is square root of f, which is equal to square root of 1 over pi integral from minus pi to pi f of x g of, f of x square dx. And this is the L2 norm. Okay, and we prove that the set of continuous function on minus pi pi is included in L2 of minus pi pi. Okay. Now a few examples. What is, for example, the norm of the function x, the L2 norm of function x? This is equal to square root of 1 over pi integral from minus pi to pi of x squared dx. And this is equal to square root of 1 over pi x cubed over 3 between minus pi and pi. And this is equal to square root of 1 over pi into 2 pi cubed over 3. And this is equal to pi square root of 2 over 3. Now, what is the norm of the function 1, the L2 norm of the function 1? This is equal square root of 1 over pi integral from minus pi to pi of 1 dx, and this is equal square root of 1 over pi times 2 pi equals square root of 2. What about if I take n to be an integer? What is the norm of cosine nx? Okay, then L2 norm of cosine nx is equal square root of 1 over pi integral from minus pi to pi cosine square nx dx. And this is equal square root of 1 over pi integral from minus pi to pi of 1 plus cosine 2nx over 2 dx. And this is equal square root of 1 over pi integral from minus pi to pi, well, 1 over 2 pi if you want, I put the half, of 1 dx plus integral from minus pi to pi of cosine 2nx dx. And this is equal square root of 1 over 2 pi. Now integral of 1 minus pi to pi is just 2 pi times 1 plus, since n is different than 0, it's an integer, sine nx over, well, sine 2nx over 2n between minus pi and pi, but sine 2n pi is always equal to 0, yes? And this is equal square root of 1 equal to 1. So the cosine nx is 1. Similarly, the L2 norm of sine nx is equal to 1. I mean, nothing changed, but here instead of plus, you put a minus. Here you have a minus, and here you get a minus, and then you get a 1. Okay. Now definition. Given an inner product space, we say that V and W are in inner product space V are orthogonal. So when are two vector orthogonal? If and only if VW equal to 0. Yeah, so it's a dot product. Two vectors are perpendicular if and only if the dot product is 0. Example, notice that the function x and the function x squared, which is 1 over pi, these are real valued function, minus pi to pi, you don't have a bar here, x times x squared dx, and this is 1 over pi integral from minus pi to pi of x cubed dx, and you are integrating an odd function over a centered interval. You're gonna use this a lot, okay? If you are integrating an odd function over a centered interval, this will be equal to 0. And now in a more interesting example, show that the functions 1 cosine n x sine mx, well, sine mx, okay, show that the function 1 cosine x cosine 2x cosine 3x sine x sine 2x sine 3x are orthogonal. So any two of these vector orthogonal with respect to the L2 inner product. So any two of these functions are orthogonal. So let's see. So you have for n equal 1 to whatever, 1 with cosine and x, so that I calculate 1 with everything, all the cosine. This is equal 1 over pi integral from minus pi to pi of cosine n x dx. And this cosine function is even, so this is 2 over pi integral from 0 to pi of sine n x dx. But this is equal 2 over pi into minus cosine, why cosine? Cosine of sine, okay, this is cosine, and the integral of cosine is sine n x over n. I can do over n because n is a positive integer, n between 0 and pi, but sine and pi is 0. You know that sine and pi is 0, so this is equal to 0. So this means 1 and cosine and x are orthogonal. Okay. Similarly, 1 and sine and x, which is equal 1 over pi integral from minus pi to pi of sine n x dx. But now the sine is an odd function over a centered interval, and this is equal to 0. Now what about for n, m, what about the cosine among each others? The cosine, cosine. Why cosine x is perpendicular to cosine 2x? So, and cosine x is perpendicular to cosine mx. So if nm is integer and n definitely different than m, cosine nx, cosine mx, this is equal 1 over pi integral from minus pi to pi of cosine nx cosine mx dx. I want n different than m because I want to take two different functions, yes? So this is equal, now notice, recall that cosine A cosine B is half cosine A plus B plus cosine A minus B. So this is equal, this dot product is equal to 1 over pi, or 1 over 2 pi, integral from minus pi to pi of cosine n plus m x plus cosine n minus m x dx. Remember, n is different than m, so this is different than 0. And n and m are positive, so this is different than 0, this is different than 0. So when you integrate, this is 1 over 2 pi of sine n plus m x n plus mx over n plus m plus sine n minus mx over n minus m between minus pi and pi. But I know that sine k pi is equal to 0 if k belongs to z. So this means this is equal to 0. So the cosine among, so I prove that the 1 and the cosine are orthogonal. The cosine among each other are orthogonal. Now what about the cosine with the sine? Cosine nx sine mx, where here nm belongs to, where nm equal 1, 2, 3, and they can be equal, doesn't matter. I'm choosing any cosine function with any sine function. This is equal 1 over pi, integral from minus pi to pi, of cosine nx sine mx dx. But now this is an odd function, so this is equal to 0. Done. So I proved that the cosine, any function of the cosine with any function of the sine will give me 0. I still have to show that the sine among each other are orthogonal. So if n equal, if n m are integer and n different than m, then sine nx sine mx, this is equal 1 over pi integral from minus pi to pi sine nx sine mx dx. And now use the fact that sine A sine B is 1 over 2 cosine A minus B. This is cosine A cosine B plus sine A sine B minus cosine A plus B. And this is equal 1 over pi to pi integral from minus pi to pi of cosine n minus mx minus cosine n plus mx dx. But now this is 1 over 2 pi sine n minus mx over n minus m. Again, this is different than 0 here, this is different than 0 here, so I can divide. Minus sine n plus mx over n plus m between minus pi and pi, but sine of an integer times pi equal to 0. Okay. So conclusion. So the function 1 cosine x cosine 2x sine x sine 2x, well cosine 3x sine 3x, and all these are orthogonal. And our question, recall our question, was, can we write f of x as alpha plus summation from n equal 1 to infinity of an cosine nx plus bn sine nx? This was our question. Which means, can I write this as f of x equal alpha times 1 plus summation plus, well, f of x equal alpha times 1 plus a1 cosine x plus a2 cosine 2x plus b1 sine x plus b2 sine 2x plus. But what does it mean? What does it mean? I considered, to reach here, I took the space of functions and I started thinking about the space of function as a space of vector. It's a vector space. So every function, you don't think about it now as a graph, you think about the function as a vector. This is what I did. And now these vectors are orthogonal, correct? These vectors, 1, cosine x, cosine 2x, and all these are orthogonal. So now, remember in R3, I can write every vector in R3. So let's remember the vector V, put scratch here, which is equal to 2, 3, minus 5. I can write it as 2 times I plus 3 times j plus minus 5 times k, where I dot j equals 0, I dot k equals 0, and g dot k equals 0. These are 3 orthogonal vectors, and this is the x coordinate or the i's coordinate, this is the j coordinate, this is the k coordinate, and these 3 coordinates are perpendicular. And then we say in this case that I, j, k, they generate all R3, correct? They say they are a basis. They are orthogonal and they generate R3. They are a basis of R3. But now let's go back to this space of functions. I have that the vector 1, cosine x, cosine 2x, cosine 3x, sine x, these are orthogonal vectors. And the question is, can I write f as a number times the vector 1 plus a number times a vector cosine times a number times a vector cosine 2x plus I have infinitely many cosine plus another number times sine x plus another number times the vector sine 2x. So what am I asking? Am I asking that these vectors, I know they are perpendicular, but the question is, does the function 1 cosine x, cosine 2x, sine x, sine 2x that the orthogonal form a basis for the vector space C of minus pi, where your alpha will be your 1 coordinate, your a1 will be your cosine x coordinate. Here your 2 is your i's coordinate, your 3 is the j's coordinate. So I transformed the question that is coming from analysis to a question in linear algebra. And this is why we did all this detour. And this detour will be very helpful to define what is alpha, what is an, what is bn, if this is true. So now let's say this. So assume the answer is yes, and let's do it the engineering way, okay? So let's say and assume what I call life is fair, okay? I can do whatever my intuition tells me, okay? This is why I'm saying let's do it the engineering way. So assume f of x is equal alpha plus summation n equal 1 to infinity of an cosine nx plus bn sine nx. What are alpha, an, and bn? So how do I isolate the 2 in this case? If I have v equal 2, 3, minus 5, how do I isolate the 2? I do v dotted with I, since they are orthogonal. You get 2i dot I, which is 1, 3i dot j, which is 0, minus 5i dot k, so you will get 2. And this is how you get the coordinate 2. How do I get the coordinate that is multiplied by the vector 1? I do an inner product, f, well, let's write it, this means f of x equal alpha times 1 plus a1 cosine x plus a2 cosine 2x plus b1 sine x plus b2 sine 2x plus. Then f of x times 1, inner product 1, is alpha 1, 1 plus a1 cosine x plus a2 cosine 2x plus comma 1 plus b1 sine x plus b2 sine 2x plus comma 1 And now I use linearity, but not really linearity with the engineering way. 1.1, this is alpha, the norm of 1 square, plus, I know that A plus B with C, this is equal AC plus BC. But what if I have A1 plus A2 plus with C? This is what I'm saying, that I will expand this, although this is just justified, but my intuition tells me this is an infinite sum. Let's try. So this is alpha 1 squared plus A1 cosine x with 1 plus A2 cosine 2x with 1 plus B1 sine x with 1 plus B2 sine 2x with 1 plus. But all these, since 1 and cosine x are perpendicular, this is 0, this is 0, everything here is 0. So you get f of x times 1 is equal alpha times norm of 1, which I already calculated. The norm of 1 is, I'm sure I did it. Yes, the norm of 1 is radical 2. So, and then you get 2 alpha. Okay. So I got that 2 alpha is equal f of x times 1, which is equal 1 over pi, by definition, integral from minus pi to pi, f of x dx. Okay. Good? This is 2 alpha. Now how do I get A1? I get A1 by doing the inner product. How do I get J? By doing a dot product with J. How do I get A1? I do the inner product with cosine x. So what I will do is, how do I get AN? I do f of x times cosine nx. So this is equal 1 with cosine nx, sorry, alpha with cosine nx plus A1 cosine x cosine nx plus AN cosine nx cosine nx plus B1 sine x sine cosine nx plus B2 sine x cosine nx plus. Now this is 0, this is 0, everything is 0, and this is 0. They are orthogonal, we prove this orthogonal. The only term that survives is the following. So this is equal AN cosine nx cosine nx, which is equal AN times norm of cosine nx squared, which I proved above, that is equal to 1 and is equal to AN. So then you will get AN to be 1 over pi, well, to be f of x cosine nx. So AN will be 1 over pi integral from minus pi to pi of f of x cosine nx dx. Okay, this is what my 2 alpha is. This is what my cosine nx is, my AN. What about BN? How do I get BN? I dot product. I do the dot product. This is f. I do the dot product with sine and x. So I have f of x sine and x. This is alpha sine and x plus A1 cosine x sine and x plus. Please, this is sine 2x here. Plus B1 sine x sine and x plus plus bn sine nx plus plus plus. Now this vanish, all the cosine vanish, all the sine vanish except this one. So this will be bn sine nx, which is equal bn, the norm of sine nx squared, and this is equal to 1, and this is equal to bn. Then bn will be equal f of x sine nx equal 1 over pi integral from minus pi to pi, by definition f of x sine nx dx bn. So if everything is nice, so if the Fourier question was correct, if I can write every function, well, of course you cannot, but if I can write every function as a linear combination of sine and cosine, then your alpha will be this one. This is your alpha, where your 2 alpha will be this one. Your an will be this one, and your bn will be this one. Then, this is a definition now, motivated by all the above. Definition: given f in L2 of minus pi, we define the Fourier sum Sn of f Sn of f of x to be a0 over 2 plus summation from n equal 1 to infinity of an cosine nx plus bn sine nx, with what is now a0 over 2? a0 over 2 is your alpha. So a0 is your 2 alpha, and my 2 alpha is this, with a0 equal a0 is 2 alpha, so this is f, then a product with f with 1, and this is equal 1 over pi integral from minus pi to pi of f of x dx. An is the inner product with f with cosine nx, which is equal 1 over pi. It's an inner product. F is an L2. I can do the L2 thing. F of x cosine nx dx. And b sub n equal f sine nx equal 1 over pi integral from minus pi to pi f of x sine nx. This is a Fourier sum. It's a finite. Oh, sorry. I'm very sorry. It's a finite sum. Okay? I define the Fourier sum to be this way. Why I define it to be this way? Because I know that if Fourier was correct, then this series should converge, this sum should converge to my original function. Because my intuition tells me that if what I'm saying is correct, that every function can be written as a linear combination of sine and cosine, then this is how it should be written. So this is this is the value of the coefficient if I was right. Okay, it's a big if that wasn't answered until the 20th century. Okay, so your a0 will be this. Okay, so the Fourier series of f, which is fs of f at x, is equal to the limit of the Fourier sum Sn of f at x, and this is equal a0 over 2 plus summation from n equal 1 to infinity of an cosine nx plus bn sine nx. But please, this is a limit, so my not make sense. This always makes sense. The sum always makes sense. Now I take the limit, might not make sense, but anyway, I call it, this is the Fourier series of f. And the question is, does Fourier series of f at x equal to f of x? This was an open problem for a long time. Okay? This is not a trivial problem. It's in the 20th century that this was proved by a field medalist. It was a very difficult proof. Okay, but I mean, we will take it in very specific cases. This was proved in 1967 on L2 of minus pi. We'll just give the theorem on differentiable function in this course. Okay, so now we are ready to do more examples, and then we're gonna answer this question for a special class of functions. Thank you.